All right, let's jump right in. Today, we're talking about three of the most fundamental things in RF propagation: reflection, refraction, and diffraction. These are really the core physics that decide how a signal actually makes its way through the world.
Hey everyone, welcome. So, this explainer is built for you, the RF technicians and engineers out there in the field. What we're doing today is breaking down part 8 from a really detailed 20-part report on radio frequency propagation. It's from the RFI detectives, who are part of Virtualization Options LLC. We're going to focus just on what's in this chapter, which is all about how our signals really behave out there.
Okay, so let's start with a question that every single one of us has dealt with. In a lab or on paper, RF signals travel in a nice, perfect, predictable straight line. But we all know from being out in the fields that that's pretty much never what happens. So the big question is, why? Well, the answer is actually pretty straightforward. It all comes down to just three fundamental ways that a radio wave interacts with the physical world around it. And if you can get a good grip on these three, you can pretty much analyze any RF path issue you're going to come across. And here they are, the big three. The easiest way to think about them is with these simple keywords. You've got reflection, which is the bounce. You've got refraction, that's the bend. And then you've got diffraction, which is the curve. Bounce, bend, and curve. Let's dig into each one. First up is reflection. I kind of like to call this one the echo effect, and you'll see why in just a second. So the textbook definition is pretty clear. Reflection is what happens when a radio wave hits a surface that's large compared to its own wavelength. When that happens, it just bounces right off. Think of it like a tennis ball hitting a wall or light bouncing off a mirror. Same idea. So what kind of surfaces are we talking about in our world? Well, they're everywhere. We're talking about buildings, the ground itself, hills and mountains, large bodies of water, and basically any big man-made thing you can imagine. These are the mirrors in our RF environment. So why should you care? What's the impact? Well, all of that bouncing is what creates multipath. The signal that actually gets to your receiver isn't just one clean signal. Nope, it's the original signal plus all of these reflections, echoes, that are all arriving at slightly different times. And that's exactly what gives you headaches like signal fading and interference. All right, let's move on to number 2, refraction, or what I call the bending effect. Now, this is different from reflection. Reflection is a bounce off of something. Refraction is the bending of a wave as it passes through something that's changing. For us, the classic example is the atmosphere. You've got all these layers of air with different temperatures and humidity. Well, that changes the density, and that change in density is what causes the wave to bend as it travels. And this bending has some really interesting effects in the real world. Sometimes it can actually help us out. It can bend the signal over the horizon, extending our range. But it can also be a problem, causing signals to bend too much and completely overshoot the antenna they were meant for. It's a real double-edged sword. And that brings us to our third and final one, diffraction. This is the curving effect. Now, this one is really cool. Diffraction is the reason radio waves can do something that seems impossible. They can actually bend or curve around the edge of a solid object. This is the whole reason non-line-of-sight communication is even possible a lot of the time. Just think about it. You've definitely had this happen. You're getting a signal even though you know for a fact there's a huge building or a hill sitting right in the path. That's not some kind of fluke. That is diffraction at work. The edges of that building are acting like a new source, basically re-radiating the signal into the area behind it. Okay, let's pause here because this is a really important point and people get these two mixed up all the time. Refraction and diffraction both involve bending, but they are not the same thing. Refraction is bending through a medium, like the atmosphere, because its density changes. Diffraction is curving around an obstacle, like a building that's in the way. One is about what the wave is traveling through, the other is about what's blocking its path. So, we've got the bounce, the bend, and the curve. Let's put it all together now. Why is this stuff more than just physics trivia? Why is it an absolute operational necessity for us? Because pretty much every important decision you make depends on this stuff. When you're calculating a link budget, you have to account for losses from reflection. When you're creating a frequency plan, you've got to think about how refraction could cause interference. When you're planning where to put an antenna or trying to figure out why a signal path is failing, you're thinking about diffraction. This isn't academic, this is the job. And this quote from the RFI detectives report we're referencing just says it all perfectly.
For RF technicians and engineers, understanding these mechanisms is not an academic exercise, but an operational necessity. At the end of the day, these principles, bounce, bend, and curve, are the tools you use to make wireless systems actually work in the real, messy, complex world we operate in.